All right, so I wanted to go over these things you worked on in class so that we weren't taking class time to do it. So let's get started. Okay, so in this problem, we have these blocks that are connected and they're going to accelerate in this direction. So the 8 kilogram block accelerates to the right, the 6 kilogram block accelerates down. And we're asked to find the work done by the force of gravity. So I'm going to number these masses 1 and 2. I'm going to do that partly because I'm trying to get you to do this more, where you label the masses when you have more than one, because it gets really confusing when you combine your equations and nobody's really listening to me yet. So I'm just drawing the force of gravity that's acting on these two blocks. And then I want you to think about how the displacement compares to that force, where this is important here because we see that the 8 kilogram block moves to the right and the 6 kilogram block moves down. So for this block, there's no work done by gravity because of the fact that the angle between them is 90 degrees between the force and the displacement, and the cosine of 90 is 0. But in this case, the displacement is in the direction of gravity, so that gravity does work on that block. It doesn't do work on the 8, and so we would pick option D. Okay, so then we're talking about a ball that goes up, then it comes back down, and again, we want to talk about the work done by gravity. mg is the force that's going to act on this ball the whole time. And we can notice that on the way up, they're in opposite directions. Another way to think about it is the angle between the force and the displacement is going to be 180 degrees, and the cosine of 180 is equal to -1. So it's going to be work is negative going up. Coming down, the displacement and the force of gravity are in the same direction. Another way of saying that is the angle between the two is 0, and the cosine of 0 degrees is 1. And so the work is positive. So we just look for the answer that corresponds to this, and that would be the last one. The work done by gravity is negative while the ball travels upward, and the work done by gravity is positive as it goes downward. This seemed to be confusing to people, and I get it. In reality, in this situation, we're looking at an action-reaction pair. The cable is pulling up on the elevator with a tension, but in reaction to that, the elevator pulls on the cable. So I'm calling that T prime, and T prime are an action-reaction pair. I think just because we simply have never talked about that reaction to the force of the tension, it seemed kind of confusing. And so if the elevator is going up, you can see that the cable tension is in the same direction as the displacement. And so that would be positive work. But the elevator is exerting a force downward as the elevator goes up. And so that's going to be negative work. So that is going to correspond to option B. Okay, now this problem, I'm going to kind of go to town on it because I want to show you a bunch of stuff about the work done by gravity and different ways we can think about it. But first, let's do some of the easy pieces. So I'm going to draw a picture of our box on the inclined plane. First of all, I want to just point out that the 128 newtons is actually the weight of the carton. We might not have really caught that initially, might have just glossed right over the newton. But yeah, that's the truth. we're applying a force of 72 newtons. And then the block is going to move 5.2 meters up the incline. So those are the forces. I might want to introduce I'm going to draw my axes. This is 30 degrees. And then I'm going to add just the normal force because we're going to talk about it. Okay. So this is a case we're still working with constant forces, and we can use the definition of work. So let's approach this by looking at the force, the displacement, and then also keep in mind when I do the calculations, I'm doing the magnitudes of those two values times the cosine of the angle between them. The rope is really simple because the displacement and the force are exactly in the same direction. So the work is just 72 times 5.2. If you wanted to think about the angle between them is 0. And we already talked about the fact that the cosine of 0 is 1. But you could have just said it was 72 times 5.2. This ends up to be 374.4 joules of work that were done. Now, because I want to talk a lot about the work done by gravity, I'm going to skip on to the normal force. And here we see that the normal force and the displacement are perpendicular. So it's the normal times 5.2 times the cosine of 90 equals 0. Just so if you wanted to do more, we could have looked at forces in the y direction in order to find out how big the normal force is. And so we could have written it as this, mg cosine of 30, because that's all the normal force, times 5.2 times the cosine of 90. It doesn't change anything. And then also, again, I just want to point out, mg is 128 newtons. We shouldn't be surprised that the normal force doesn't do any work. It actually doesn't move the box in its direction. And so it makes perfect sense. So now let's look at gravity. So what I drew here is I just wanted to focus on the idea that we're trying to find the work done by the force of gravity. And I'm going to look at it 3 different ways. I'm going to say, first of all, the work is force times displacement times the cosine of the angle between them. When we look at the work of gravity, we can use this in a very plug and chug kind of way. We have mg times the displacement, and then the angle between them is going to be this angle, which is 30 plus 90, which of course is 120. And I'll get minus 332.8 joules. And so that was like plug and chug approach. Now, one of the things that I mentioned is we could think of it as the force of gravity that is parallel to the displacement. If we break gravity down into its x and y components, mgx would be the one that would be parallel to the displacement, although it's in the opposite direction. And so we could say mgx times 5.2, and then just to emphasize the fact that they're in opposite directions, it would be the cosine of 180. So this would be mg times the sine of 30 times 5.2 times the cosine of 180. And this should also give me minus 332.8 joules. And then finally, one thing I didn't talk about is we could look at it as the force of gravity times the displacement parallel to the force of gravity. And that's where we're just taking Fs cosine of theta, and we're sort of linking these two, because then this is the component that's parallel to F. So I'm going to redraw the triangle. And so as the box moves from here to here, so this is 5.2, this is 30 degrees, and then this right here is the S parallel. That's the displacement that's parallel to the force of gravity, which is vertical, and this would be given by 5.2 times the sine of 30. And so if we found the work done by gravity doing that, we would get mg times 5.2 times the sine of 30. And then because they're opposite, because the force of gravity acts down, but the thing moves up, we have that 180. And again, it's going to be minus 332.8. So I just like to give you the opportunity to look at this different ways, because probably one of them clicks, and then that gives you get, okay, well, now that one I get that. Finally, when we find the net work, we just add the 374.4, which was the work done by the rope, minus the 332.8, which was the work done by gravity. And it's a difference of, I calculated that wrong, I think. 41.6. And we'll talk about what the consequences of this being a network mean next class.